All right, so we have been looking at our acids and bases and kind of starting to relate them back to Kw. We know that if we compare our acid with its conjugate base and put those equilibrium together, Ka times Kb will always equal Kw, which means if we know one of them, we can divide by our Kw by the one we know to solve for the missing species. And all that to say, really, if it is the conjugate of a strong species, it is a weak base. If it is the conjugate of a strong base, it is a weak acid. That there's this inverse relationship between the acid and base pairs and their relative strengths. And so I know you're looking at this, you're going, okay, that's fine, but what does that really mean? Well, what this means is that when we start to think about some of our species as they dissolve in the water, we need to be cognizant of whether or not a reaction will take place with one of these species in water. And so if we were to think about some salts that we can start to throw into solution, different salts will actually have different effects on the pH of the solution. And that's because we've still got this water, this amphoteric water that could be both an acid or a base, that could change depending on the strength of the salt that we put into it. Now, some of them, if we put them in, they don't change the pH at all. Examples of this would be our chloride ion or our bromide ion. In terms of our cations, it would be things like lithium or sodium. When these ions get associated into water, they have no measurable effect on the pH of the solution. And this makes sense. If we were to think about what they would do if they were to react with water. So for example, let's go ahead and we'll look at chloride. If chloride were to try to react with the water, well, this is a negative anion, it's going to attract the hydrogen. The particular or the type of reaction we would see is we'd see kind of this hydrogen getting displaced, coming over and attacking or attaching to our chlorine and leaving behind an OH minus. Now, come on, y'all. We got hydrochloric acid. That's a strong acid. And we end up making a hydroxide. That's a strong base. We know that our favorability or our equilibrium will always favor the weaker side because the bonds are stronger. And so this would never happen. We'd never see a change in the pH of the solution when we add a chloride because these would never want to exist. They dissociate, especially for hydrochloric, they dissociate 100% of the time. And so we'd say over here, yay, with our neutral water. Same thing if you come down and look at one of our cations. For example, if our lithium ion were to try to react with our water, we would see, okay, so the lithium would try to get with our hydroxide, leaving behind an H plus in solution. Now, come on, y'all. Group 1 hydroxide, that's a strong base. H plus is our strong acid. This would never happen. We would favor the left, and we would see, again, no measurable change in the pH. But when we look at the conjugates of strong species, now all of a sudden, the conjugates of weak species, now all of a sudden we start to see a change in the resulting pH of the solution. One we should look at here would be our fluoride ion. So if we were to throw some salts, so for example, sodium fluoride into solution, the sodium ain't going to do squat, but the fluoride is going to affect the pH. The reason being, when our fluoride interacts with our water, we end up making hydrofluoric acid, which should jump out to you. This is one of our very weak acids. And so we end up making this hydrofluoric acid and leaving behind a hydroxyl group. Oh, all of a sudden we've made this species, this was a weak acid. That means this is a strong conjugate base. As a result, we end up seeing this shift, and we actually get some of this in solution. And because we've got some hydroxides formed, we end up making a slightly basic solution. We can change the pH just by changing some of the ions in solution. Now the good news is, as we look at these are all conjugate bases for weak acids. So we end up making this strong bond, leaving a hydroxide behind. And this would also occur if we were to add something for example, this aluminum complex ion, we'll come back to that here in just a second, because this is a little funny to think about what actually happens with what we call our ligands and our kind of adducts, but more on that here in just a second. If we want to think about what happens for our acidic species, yeah, we know we got this HSO, well, let's do this HSO3. That would be the conjugate of sulfurous acid. Ooh, sulfurous acid is weak, which means its conjugate base, based on our relationship with Kw, would be stronger. When we throw this into solution, it ends up attacking that water, and we end up forming our weak, sulfurous acid and a hydroxyl group again. And because this is a weak acid, we know its bonds to be strong. It wants to stay intact, and so we have some of this hydroxide left over. And while it's not a huge, nope. Reverse that, flip it back, flip it back. What we'd end up seeing here, we've got this species. It would form our sulfite ion and our hydronium species. I apologize, that's a big mistake. As a result, we end up being a little more acidic in solution. We also see some of this happening with our aluminum hydrate species. We'll again kind of look at that here in just a second. If we think about our ammonium species and what it would do with water, again, we have a species, NH4+, that can donate a hydrogen, and all of a sudden we've got a hydronium species floating around and this nice, very stable ammonia molecule. And so as a result, when we have just, for example, ammonium chloride in solution, we work with that one quite frequently. Your ammonium chloride goes into solution. The chloride doesn't change the pH any. It doesn't try to form any species, but our ammonia actually gets formed over the result of this hydration process, or autoionization process with our water. Now, when we look at these kind of complex ions, it gets a little tricky. Please note, I would never ask you to start to predict these, but it is a little more difficult when we start to look at these changes. Cool, so kind of general rules of thumb when we start to think about these, because there's a lot of these, but we can kind of pull out some trends or some patterns. Anions that are conjugate bases of strong acids, for example, chloride or nitrate. If you were to add an H, it becomes hydrochloric. That's strong. This becomes nitric. That's strong. Doesn't break apart, stay the way they were. They are going to have no measurable effect on our pH. So if it's the conjugate base of a strong acid, it's weak. It doesn't react. Alkali metals, alkaline earth metals, their cations also have no measurable effect. And this makes sense. This goes back to when we think about our strong bases, group 1 Castor Bear, those are strong bases. That means their conjugate, just the cations, are relatively weak. They don't want to react. Things such as carbonates, anions of carbonates that are conjugate bases of weak acids will raise the pH of the solution. If we add a carbonate into solution, it gobbles up some hydrogens, strong bonds there. As a result, our water becomes basic or higher on the pH scale. It raises the pH of our overall solution. Acidic cations are metal cations, so things with a 2+ or 3+ charge, and our ammonium ions. So for example, our iron 2+, iron 3+. We also got things like aluminum, or we can have our chromium 3+. All of these can react with water and get hydrated with our water to form these complex ions, which actually end up changing our pH. And so there's a couple different ways that this can happen, but these are going to start to change our pH as well. So when we look at that kind of hydrated species, so we end up seeing is in three-dimensional space, because we've got this aluminum ion, it's got empty orbitals available to it, and so it can act as a Lewis acid, accepting some electrons. Our water molecules can act as Lewis bases, donating some electrons, and we end up with these coordinated covalent bonds. And it is three-dimensional, so that's why we've got kind of three different areas of attack here. Again, I would not ask you to predict this, but just understand the concept of why this does what it does. And so after we kind of throw our aluminum to water, our water's crowded around. We can see the negative oxygen side coming up next to the positive aluminum side, and that's where we see our dissociation as well. And as a result, because this positive charge is pulling on these electrons, as it pulls on these electrons, it actually starts to weaken these hydrogen-oxygen bonds. And as a result, if we have a nearby water molecule kind of coming up near here, we can actually see a breakage of our hydrogen. So one of these H's will actually pop off, get attached to form our hydronium, leaving behind a hydroxyl group that wasn't there before. So we had 2 hydrogens here before, now we've lost one. And as a result, our solution has now become lower on the pH scale. It's become more acidic. Again, I would never ask you to predict or try to quantify what these kind of ligand pairs are. I just want you to understand how these can also affect the pH, even though you look at aluminum 3+, you're like, man, acid, bad, what? Going back to our Lewis definition and how we can define our electron acceptors and donors. And it turns out, we'll do a little practice here, and then we'll kind of look at why this becomes important chemically. So yeah, we've got a couple examples here. Go ahead, pause it real quick, give it a shot, and then we'll kind of walk through it. Or I guess you could just walk through it and listen and learn, your choice. Or you could listen through it. You can try it yourself, listen through it, and then rewind and try it again. Yeah, okay, whatever. Whatever makes you happy. Cool. So let's take a look at what we would split apart into. We put this into solution. Woo! We put this into solution. We got to think about what ions are going to be floating around in that solution. We're going to have Ca2+ and some Cl-. Yeah, we'll have 2 of them. We're not really worried about that. We're saying we've got these ions. They're apart. What will they try to do with the water as they start to react? Well, if this reacts with water, this is positive. It's going to be trying to form our calcium hydroxide species, leaving behind, calcium hydroxide. Wait a minute. Calcium hydroxide, strong or weak? Pretty sure that's strong. That's not going to form. As a result, it stays here. Cool. So that has no effect. Chlorine, we already kind of looked at on the previous example. If this reacts with water, it's going to make hydrochloric acid and a hydroxyl group. Not going to happen. Those are both strong. I'm going to favor the left-hand side. So this would remain in solution neutral. We would see no measurable change to the pH as a result of these 2 in solution. Cool. Next one here, we got NH4 and our bromide ion. This could react with water to form H3O+ and NH3. Ooh, both of those are super stable. NH3 we know to be favorable. This is conjugate. Okay. If we were to react with water here, we end up making hydrobromic and a hydroxyl. These are both strong. That ain't going to happen. But this one will. Oh, okay. If this happens and we end up making some ammonia molecules, we'll have some extra hydronium floating around now. And so this will be an acidic solution at the end. Cool. Ooh, here we got one of those complex ions. Going to talk through what happens here. Because we've got a weakening of the water molecules, it can pop off one of those H's to form more hydroniums. This is going to become slightly acidic in solution. Cool. If we think about what could form here, we got K+, NO3-. Well, that's going to try to turn into nitric acid. Going to stay over here. That's strong. Stays over here. That could try to turn into potassium hydroxide. That's strong. Going to stay over here. So we are neutral once again. Cool. Now we got this little dude. All right. Potassium. That's going to try to form potassium hydroxide. Ain't going to form. Then we got HCO3-. Ooh, bother. This is amphoteric. We could write this one of 2 ways. It could react with the water to try to form some acid particles. It could react with the water to try to form some base particles. This could both donate or accept a hydrogen. It is amphoteric. If we think about this, though, this is the direct conjugate of a weak acid, which means it is a stronger conjugate base. As a result, it's going to act more like a base, accepting hydrogens to turn into H2CO3, leaving behind some hydroxides in solution. This is going to be a resultingly basic solution with extra hydroxides now floating around in that aqueous solution. And the reason why we care, the reason why this is important to kind of note is the lie we told you once upon a time when we looked at our titration curves. Once upon a time, we looked at the pH and we said we get this magical spot where we've got the moles of acid equaling the moles of base, and as a result, we are at the equivalence points, equal moles of both. And we found that there's a unique trend or pattern that happened when we looked at our different types of titration curves. If it's a strong acid and a strong base, this equivalence point is right where we would expect it. We've made perfect neutral water, and as a result, our pH is 7. And last year, we tried to explain that if you have a strong base with a weak acid, if we have a strong acid with a weak base, starting at low pH, we end up down below that equivalence point. We get pulled towards that strong acid side, which is true, but the reason we explained it is not quite so true. If we have a weak acid conjugated with a strong base, we have our equivalence point of greater than 7. And again, this is true. This is chemically what happens during these titration curves. The reason why is because of the conjugate species. So for example, if we look at kind of this last example, and we think about what is in the solution. At this moment, at the equivalence point, we had originally some weak acid, we call it HA. We have added an equal number of moles of hydroxide to change all of that HA into A-. We've neutralized all of it. It has all changed into its conjugate species. But here's the kicker. Because now all we have floating around in solution is this A-, there's only one other reactive species in the beaker for this A- to react with. And it's the thing that we have billions and billions and billions of molecules of, the water. And so what actually ends up happening, yes, we are at the equivalence point, but because there's water present, we actually have a reautoionization. We end up forming some of that weak acid again, because if this is a weak acid, it's got a strong conjugate base, it wants to react to make some of that weak acid again because it has strong bonds. And when this happens, we end up leaving some hydroxides left over. And that's why at this equivalence point, the pH is greater than 7, because we now have some extra hydroxyl groups floating around. Same thing ends up happening if we look at a strong acid with a weak base. We end up seeing that that weak base, once neutralized, tries to react back, leaving some extra hydronium reformed from the water as it reautoionizes. And that's actually why we see the graphs kind of shifting the way that they do, because of this now reactive particle that we've left behind in solution. Cool. This kind of brings us to a wrap on chapter 18. Be looking for some additional practice coming your way as we start to prepare for wrapping up this part of our studies. Have an awesome day, guys.